If I could have everybody's attention and welcome everyone to one of the main highlights of the VGP section, which is the Bowen Award lecture. I'd like to just perhaps mention that this is actually a particularly propitious day in the, if you like, in the Bowen Award. I believe that it's 100 years since Bowen actually submitted his PhD, or published his PhD, so that's quite a landmark in the world of igneous petrology. And to deliver this year's 2012 Bowen Award lecture, it's my pleasure to welcome Yoshiyuki Tatsumi, who's this year's awardee. Before saying something a little bit about Yoshiyuki, I'd like to just perhaps remind people that it is the VGP reception this evening, which is where the award itself will be given, and that starts at 6:30 in Salon 9 in the Marriott Marquis, so please everybody come to that. Very briefly, I'll say that Dr. Tatsumi's award was unanimous by the VGP Bowen Awards Committee as an outstanding contribution, and I'll just read the citation for you. Dr. Tatsumi has made numerous fundamental contributions to our knowledge of magmatic processes and their role in understanding the evolution of the Earth's crust through laboratory experiments, field-related petrological studies, and associated modeling. He has been central in advancing our knowledge of magmatism and hotspots and subduction zones, especially the Isotopic intra-oceanic subduction system and transport processes in the Mantle wedge. So without ado, I'll perhaps ask Dr. Tatsumi to the stage to receive a certificate for the lecture and congratulations of the VGP section for his achievements.
Thank you, Stephen. It's really my great honor to receive this award. Okay, thank you. Okay. Actually, my first target in my career as a magmatologist is a high magnesium andesites in a small island in southwest Japan. These rocks are very interesting because they are unusually and characteristically derived directly from the mantle. Since then, my interests have spread more general arc and hotspot magmatism. And what I'm going to present here in this talk is the role of subduction zones and the evolution of this planet Earth. Okay, here is a menu of this talk. So first of all, I would like to emphasize this planet is shore planet as well as water planet. And second topic is how to make the shore or the continent. And the answer in my talk is the continent is born in the ocean through plate tectonics. And the third topic is the reason for operation plate tectonics solely on this planet Earth. And I would like to emphasize water is a very important role in Earth evolution. Okay, so as you know, our planet Earth is a water planet. And actually, the water covers more than 70% of the Earth's surface, and weighs a lot, about 10 to the power to 18 ton. And water must play key roles in the evolution of the Earth system. But on the other hand, we have very characteristic topographic feature on this Earth. We have bimodal height distribution. The horizontal axis is height, and the vertical is a fraction. And we have lowland, we call it ocean, and we have highland, and we have bimodal distribution here. And highland is called shore or the continent. Okay, how about other terrestrial planets? Okay, here we have Venus and Mercury surface height distribution. They have very unimodal height distribution at the surface. And Mars has apparently bimodal distribution like this way. But this may be caused by inconsistency between mass center and the morphological center. And so if we eliminate the long wave component of this effect, the Mars has actually unimodal height distribution. So in terrestrial planets, the Earth is the only planet which has bimodal height distribution, lowland and highland. Okay, so the Earth's surface is composed of continent and ocean and show very uneven surface structure. On the other hand, other terrestrial planets show very even or smooth or uniform surface. Okay, what's the difference between these highland continent and lowland ocean? Of course, the main difference is the presence and absence of water. But underneath the water, we have quite different crust from the continental crust in the oceanic regions. Okay, the height of the continental crust of shore is average 850 meters, and the ocean is about 4,000 meter depths. And the thickness of the crust is different. The continental crust is much thicker than the oceanic crust. And composition is also different. So the compositional difference and this thickness difference causes highland and lowland, that the density contrast between these two crusts, continental crust and oceanic crust. So why we have this kind of compositional difference in these two regions, continent and ocean? Okay, so here is a comparison between organic andesites and continental crust composition. Data from Northeast Japan arc and the silica versus some other element data. And the blue guys indicate calc-alkaline rock series, and the red one indicates thoracic rock series. Okay, here we have a estimated composition of bulk continental crust and yellow. So it's clear that the bulk continental crust has calc-alkaline andesite compositions. It is also true for trace element compositions. So Northeast and Japan andesite, especially calc-alk andesite, show very similar patterns, trace element patterns for average continental crust. So the important compositional feature of the continent is andesite. So the origin of andesite is key to understand the origin of continent and also origin of highland in this planet. Okay, so andesite is one of the major products in subduction zones. So the people believes, or most of people believes, continental crust was born in arc, and in contrast to this continental crust, oceanic crust was believed or proved to be born in mid-oceanic ridges. So anyway, these two types of crust, land and the ocean, or highland and lowland, was produced by plate tectonics. Okay, but we have a dilemma here. But in most subduction zones, we have primary magmas that is partial melting product of mantle wedge is basaltic in compositions. But major product in especially continental arc is andesite. So we need some process to form andesite from the basalt. So that is the next topics in my talk. Okay, so I would like to introduce project IBM. So this is an example of combined seismic and magmatological studies. So here we have IBM, is born in Mariana Arc, not a computer company. So here, this is born in Mariana Arc. So this is a juvenile intra-oceanic arc that extends almost 3,000 kilometers from the East Peninsula to the Guam Island down here. And the very characteristic feature of this arc is a crustal structure. So this IBM arc has a middle crust with a BP of 6 kilometers per sec. So the meaning of this value will be discussed later. And this arc is very characteristically collides with the Honshu archipelago here. So that means we can see some deeper structure of this intra-oceanic arc in the land region here. Okay, here there is a tectonic evolution of the IBM. The IBM arc was born about 50 million years ago in the equatorial regions here. And at about 50 million years ago, we have a four-arc magmatism and ophiolite formation in this arc. And then subduction initiated soon after the formation of this arc at about 47 million years ago, causing very characteristic arc magmatism, including bowenite, an example of high magnesian andesites. Okay, after that, about 25 to 50 million years ago, we have a back arc rifting here in this region, and this causes separation of Kyushu parallel ridge and East-Bonin Mariana arc, and here. So East-Bonin Mariana arc move eastwards from away from the Kyushu parallel ridge. And at about 15 years ago, we have Japanese opening, and in association with this back arc opening, South Japan arc rotated clockwise, and after that, this East-Bonin Mariana arc collides with Southwest Japan arc in these regions. And we have again rifting here in this Mariana Trough since 6 million years ago. This is a very brief summary of the tectonic evolution of IBM. Okay, so let's introduce seismic imaging results of IBM arc. So we've done using these weapons. And this is lines we surveyed. So many lines anyway. So I would like to show some results in the across arc section in the blue, and also along arc section from north to south in 2 lines. Okay, here I will show across arc structure of the crust and the mantle. Okay, now spring. And green region is it must be focused here. So this is because this is very characteristic VP regions that is about 6 to 6.5 kilometers per sec. Okay, this is along arc section from north to south. From north to south, okay? So also here, we have a green region that have a seismic velocity, P-wave velocity structure about 0.56 kilometers per sec. So we have very wide range of middle crust formation in this IBM arc. Okay, I would like to summarize characteristic seismic structure in this IBM arc here. Okay, the first one is a VP structure in the middle crust. So the value 6 to 6.5 kilometers per sec is identical to bulk continental crust with intermediate composition. So that's the reason why here we have andesitic continental crust formation along this arc. Also, lower crust has a rather high velocity structure like this value. And then below Moho, we have low velocity uppermost mantle. The value is about below 8 kilometers per sec. So 8 kilometers per sec is a normal value or average value for the uppermost mantle below the Moho. So we have low velocity uppermost mantle in the subduction zones. And also, we have reflectors here. One characteristic reflector is a Moho. Okay, and second one is second reflector is distributed within the mantle, immediately underneath low velocity uppermost mantle regions. Okay, so this is a summary of the seismic structure in this arc. Okay, so now I would like to discuss the origin of characteristic middle crust, possibly having andesitic compositions. But one possible mechanism to form such a characteristic VP structure is a mantle-derived mafic Pluton underneath very high temperatures. But the temperature is unlikely high. So I do not believe this mechanism for the formation of middle crust structure. Okay, so the second mechanism is the intermediate compositions or intermediate Pluton, and which forms middle crust. And one candidate for such andesitic composition is the mantle-derived boninite. However, boninite is normally or generally water-rich, and that causes very high VP values for these Pluton because of the presence of amphibole in this Plutonic rocks. So this is much higher than the observed value. So we would like to test or examine the mechanism including differentiation of mafic rock and also such a or demelting of such a mafic crust and magma mixing processes to form characteristic middle crust. Okay, so here is a very simplified model. We have basaltic crust or initial arc basaltic crust here, and moho is here. Then we have underplating basaltic magmas immediately below the moho, and that causes partial melting in these regions. So such a partial melt may mix with basaltic magma to form andesite, or directly partial melting product may be andesitic in compositions. And then the melt migration upwards and then form a middle crust in these regions. Okay. Okay, based on this model, the crustal component include these four layers. One is upper crust, middle crust, and lower crust. And we have a residue after partial melting of the lower crust. So these regions should be called crustal component. Okay? But moho is here. Moho is here, and probably we may guess moho may be distributed here or here. Okay, let's consider about this position of the moho by using a petrological examination of seismic structure. So for petrological examination, we use the composition of IBM arc, or especially northern part of IBM arc. So here is a spherical versus MGO diagram that shows the compositional variation of the IBM rocks in gray spots. And based on these chemical variations, we assume primary basalt magmas, and we selected a very averaged or normal basaltic composition or andesite compositions and rhyolite composition here. And also, we need some melting regime for this basalt. We conducted high pressure experiment, not really high pressure, crustal pressure experiments for an IBM basalt. And these are some results of those melting experiments: melting fraction versus silicon composition and ion composition. And also, this is AFM diagram. So based on this AFM diagram, IBM andesites may be produced by very hydrous conditions. But petrologically or petrographically, we have evidence for magma mixing only for calc-alkaline rocks in this IBM arc. So the likely process for formation of andesitic or andesitic magmas and IBM arc is a mixing between mafic and felsic magmas rather than the hydrous differentiation of basalts. Okay, here is a comparison of the volume of melting products of the lower crust of basaltic component. Okay, here we assume the middle crust or andesitic composition was a mixing product between crust-derived felsic melt and mantle-derived mafic magmas. And then if so, we have to assume the lower crust is composed of remaining initial mafic basaltic crust. Okay? Then we have excess crustal component below moho that is composed of Restite, melting residue or Restite, and the Cummulate. So roughly speaking, volume of these excess crustal component is about 5 times thicker than the middle crust. I mean, this excess crustal component is required for producing middle crust in these green regions. Okay? So the volume of these excess crustal component 5 times larger or bigger than the middle crust component. So that means, okay, I should say this excess crustal component is distributed below the moho. So in terms of seismologically, seismic definitions, this crustal component is distributed in the mantle, but this is crustal component, okay? So that means moho is transparent and transformed, and crustal component must be transformed into mantle across the moho. So we would like to propose moho is not a rigid boundary, but it is transparent and permeable for the crustal component. Moho is, as you know, a sharp seismic boundary and exhibiting very velocity jump from 6 to 7 to over 8 kilometers per sec. And moho defined the crust mantle boundary seismically. And this boundary is generally accepted as a rigid lithological boundary, gabbro-peridotite boundary. But as I mentioned before, and at least for IBM arc, we have crustal component below the moho or in the mantle. Okay, so let's introduce the nature of the moho in IBM region. Here we have a backpack region. We have very normal moho. This is a VP values. So from 7 kilometers per sec to 8 kilometers per sec, here is a moho. So this is very normal moho. But underneath arc, we have low velocity regions in the upper mantle. So as I mentioned before, this is very characteristic feature generally for the intra-oceanic arcs. Okay, so I would like to examine such a crust mantle structure in terms of petrological modeling. So to do so, we need a phase equilibrium along infrared geotherm using purple X. And also, we need VP and density calculation based on a Hacker et al. Data. And also, we assume the basalt contains 0.1% water and the intermediate partial melt or andesite contains 0.3% water based on IBM tonalite compositions. Okay, this is the result of modeling. And the vertical axis is the depth, and the horizontal axis in the right-hand region is a VP structure, is a VP. Okay, and the hatched region is observed value, and the red line indicates a calculated value for VP and density. Okay, so this result shows very consistent with the observed calculated VP value is very consistent with observed seismic structure. And I would like to emphasize the density inversion at the base of the low velocity layers in the upper mantle here. The blue circle indicates that regions. So that means these crustal components or low velocity layers may be delaminated from this lithospheric mantle. Okay, so let's summarize the continental crust formation and subduction zones and this oceanic, intra-oceanic arc. So we have pre-arc oceanic crust, and then we have initial arc crust with basaltic compositions. Then we have melting and remelting and the differentiation process in this region, and we have a melting residue here underneath or below the moho in the upper mantle. So we may call this melting residue as anti-continent here, because to form continent in the green region, we definitely, or simultaneously, we have a formation of anticontinent here in the upper mantle. And important point is the melting residue has very mafic composition, and discharging this ultramafic anticontinent makes our crust composition andesitic. So that is a reason why we have andesitic composition from basaltic primary magmas formed in the mantle wedge. Okay. And so next interest is the fate of the delaminated anticontinent. As I mentioned before, this anticontinent has higher density than the normal upper mantle, so that may be delaminated from this region and down to the mantle. So in order to understand the behavior of this anticontinent, we've conducted high-pressure experiment for this composition. So this is the result, pressure versus mineral proportions. Okay, we have upper mantle, lower mantle boundary here. And this is very characteristic feature for this compositions. Appearance of the dense magnesium perovskite here immediately below the 670 kilometer discontinuities. So what the effect of this one? So here is the pressure versus density diagram for PREM, normal mantle. And this is a calculated thermally equilibrated anticontinent density profile. So anticontinent are always denser than the normal mantle in this region. And this is very contrasting features with mid-oceanic ridge basalt compositions. They become lighter in the uppermost lower mantle here, but anticontinent is always denser than the surrounding mantle. And this is also true for the lower mantle regions. So that means this anticontinent, which is delaminated from the lithosphere, fall down headlong towards the core mantle boundaries. Okay, so let's consider the volume of anticontinent, which was formed throughout the history. Okay, so we have a continent volume like this way. Then, as I mentioned before, a crustal component was partial melting product, or 20% partial melting product of initial basaltic compositions. So that means we have accumulated anticontinent of these values, these volumes, okay? 10 to 10 cubic kilometers. So that forms about 200 kilometer depth layers or thickness layers above core mantle boundaries. 200 kilometer layer above core mantle boundary is, roughly speaking, D double prime layers. So D double prime layer may be a reservoir of the anticontinent, which was delaminated from or through formation of a continental crust. Okay, so this is a standard model for the D double prime layer. So D double prime layer is characterized by the formation of post-perovskite, and also the composition may be different from the other mantles because of the involvement of the subducting mid-oceanic ridge basalts. But here we have our model. The falling anticontinent may be one of the major components in the D double prime layers. I do not deny the contribution of mid-oceanic crust or slab component, but I would like to emphasize anticomponent is one of the major components in the D double prime layer in this region. Okay, so next topic is the subduction zones as a factory. So here is a cartoon, and we have volcano here, and we have a belt conveyor that occupies raw materials into this factory. And the raw materials in this factory is, of course, oceanic materials, including sediments and MORB, and also mantle wedge material is one of the major raw materials in this factory. Okay, what's the product in this factory? So the magmas and the volatiles, and also their final solidification product, continental crust, is a major product from this factory. Okay, as other factory do, we have a waste material from this factory, subduction factory. So we have 3 waste material here. One is a chemically modified sediments, and also second one is a chemically modified and also fresh MORB, in the subducting lithosphere. And also, as I mentioned before, we have anticontinent, which was formed through formation of the continents in this factory. Okay, in turn, we have three major components in the deep mantle based on the geochemical data for the hotspot factory. And we have three enriched reservoir, EM1, EM2, and high mu. And also, we have three waste material from subduction factory. So this number three is accidental or necessary consequence or closely related with each other. So that is the next topic. Okay, in order to test such a geochemical cycle, we conducted experiments for the mobility of the element through subduction or dehydration process. Here is the result for sediments, and here is the results for altered MORB or hydrous MORB. And based on these data, we can calculate the isotopic evolution for the chemically modified sediments and also chemically modified mid-oceanic ridge basalts. Okay, so here is the results. We have a sediment component which was formed about 1 billion years ago or 2 billion years ago, show strontium and neodymium composition here. And these composition may reasonably explain the enriched mantle composition EM2 end members. Okay, so dehydrated sediment may be the source for EM2 component in the deep mantle. Also, mid-oceanic ridge basalts, including a fresh portion and dehydrated portion, may contribute to form high mu component in this strontium neodymium diagram here. Okay, so how about anticontinent? So this is a calculation for the anticontinent results. So we know the composition of anticontinent because of the modeling of the melting of the lower crust of basaltic components. So we can use such a data for this modeling. So this is, here is a strontium-lead diagram. So this is a continental crust, and these lines indicate anticontinent composition formed 1 billion years ago, 2 billion years ago, 3 billion years ago, and 4 billion years ago. So the EM1 component can be explained, or a chemical feature of the EM1 component can be explained by the mixing between bulk silicate earth or lower mantle component and anticontinent, which was averaged formed at about 3 billion years ago. Okay. So now we have we can say three enriched end members, and the deep mantle was closely related or products from the subduction factory. One is a chemically modified sediment, one is a chemically modified mid-oceanic ridge basalt, and third one is anticontinent. Okay, here again, cartoon of subduction factory. We have a raw material, and we have products of continental crust, and we have three waste materials: anticontinent, chemically modified sediment, and MORB. Okay, these components, three waste material, can be recycled as mantle plume, EM1, EM2, and high mu characters. Okay, so subduction factory has been operating as a zero emission factory. So we can say these waste material are completely recycled as a mantle plume component and recycled again to the surface by hotspot factories. Okay, so Project IBM show ocean creates continent. That is something like a Zen dialog, but I mean continent was created in intra-oceanic island arcs. Okay, and also another important outcome from this project is anticontinent may form DW prime layer and recycled as EM1 component in the mantle. Okay, but in our discussion, we have a basic assumption that IBM middle crust has intermediate compositions. Okay, that is probably only one assumption in our discussions. So we have to confirm these assumptions by using deep drilling in these regions. We are now proposing a ultra deep drilling in this region towards the middle crust and to understand the petrological and geochemical feature of the middle crust that may, we believe, that have andesitic in compositions. But anyway, we have to directly sample from these regions and to confirm this is andesite in composition through andesites here. Okay, so one important conclusion in this talk is continent was born and also oceanic crust was born through plate tectonics operations. So next topic I would like to emphasize is the cause of plate tectonics in this planet Earth. Okay, so to do so, we would like to briefly summarize or review the thermal structure of the deep mantle, okay, and core. So here is a cross-section of the Earth, and we have, of course, layered Earth from the mantle to the core. And also, these layered Earth, origin of these layered Earth is phase changes. And the phase boundary provide us depth and temperature relations like this way, and these discontinuities. And we have temperature profiles in these regions. Okay, so next topic we would like to discuss is engine, heat engine character for the Earth's interior. Okay, so here we have a surface heat flow of totally about 46 terawatt, and also we have a heat from the core about 8 terawatt. That is based on experimental data and also seismic measurement for the D problem layer thickness. And then we have radioactive heating in the mantle. So 46 terawatt output minus 8, that is from the core, and also minus 13 terawatt, that is caused by radioactive heating, is 18 terawatt. That is used or consumed for mantle convection. So about 40% of heat from the Earth is consumed for mantle convections. So mantle convection is a major outcome of the heat engine of the Earth. Okay, so this is a well-known simulation for the mantle convection using a pressure temperature dependence of the viscosity. And the temperature dependence of the mantle viscosity causes the lithosphere, asthenosphere boundaries. The blue region or colder color region shows the lithosphere, and yellow and green and red region indicate the asthenosphere. And so this may cause a plate tectonics like this way. But still, we do not have plate tectonics, because if we have strongly temperature-dependent viscosity in the mantle, we have very rigid plate at the surface of the mantle. So that is a stagnant lid. So if we have a stagnant lid like this way, we do not have plate tectonics. And also the mantle convection is operated only in the deeper mantle, and the surface portion of the mantle is very strictly rigid. So this is not the plate tectonics, but we have plate tectonics here in the Earth. So what's the reason for operation plate tectonics? As I mentioned, or as I emphasized, we have, of course, liquid water at the surface, and the water reduces the strength of the rock. So that may cause that is very critical in plate motion, because water reduces the strength of the crack and forms the fault in the lithosphere regions. Okay, so the role of fracture within the plate is very important for the operation of the plate tectonics. And the liquid water causes fractures in the stagnant lid, and then such a fault or a segmented plate may move by its own density difference with the mantle. So that is the operation of plate tectonics. So the one possible reason for the causing plate tectonics is the presence of the water at the surface. Okay, so as I emphasized, the continent was born by plate tectonics. Of course, oceanic crust was born as a result of plate tectonics. And plate tectonics may be operated because of the presence of liquid water at the surface of this Earth. So the next topics we have to discuss, of course, I do not have the answer for that. We need to know why this planet has liquid water at the surface. So the origin of water is probably from, derived from planetesimal and also ices from the region outer than the snow line in the solar system. And then we have very good conditions suitable for the presence of liquid water. So I mean, the mass is suitable for keep the liquid water, and also the temperature of the surface is a good condition for the liquid water. So, but we do not know that the condition for the Earth is a necessary consequence of the planet or solar system evolution or not. So that is the next topic we have to understand. Okay, let's summarize. So the answer, the question is why this planet to be the Earth? So the one of the very characteristic feature of this planet Earth is the presence of both continent and ocean, namely highland and lowland. So highland, that is a continent, was born in the ocean through plate tectonics. Also lowland, ocean or oceanic crust was born or created through plate tectonics. And plate tectonics may be triggered by mantle convection, and also the presence of liquid water at the surface is very critical for operation of plate tectonics. And the distance from the sun and the mass of the Earth are essential parameters, and the presence of liquid water. But as I mentioned, we do not know whether this presence of liquid water is a necessary consequence or an accidental consequence of the solar system evolution. That is the next topic we have to understand. Okay, thank you very much.
Well, thank you, Tatsumi-san, for a wonderful lecture, superb slides and illustrations, and beautifully clear. So I think we do have some time for some questions. Perhaps people in the audience will appreciate first that we've got two huge lights on the screen, so we can't actually see very much. And secondly, because it's a big room, if you have a question to ask, please speak up loudly. I'll go down there so I can see who wants to ask questions, and we can have 5 minutes or so on that.
So the thicker part of the Eastbourne Mariana crust along our section is located underneath basaltic volcanoes. So that is just a making up stage of the continental crust. We do not have any evidence for the delamination in Eastbourne Mariana arc. So that may be caused by the thickening of those crusts by collision with the Honshu crust. So we would like to emphasize, we would like to examine the delamination, occurrence of the delamination in those regions.
Take another question. Yes, there. Yeah, anticontinent has more amorphic composition than the mid-oceanic ridge basalt, but we do not identify which kind of physical properties at the D prime layer, or I mean the difference between mid-oceanic ridge basalt component and the anticontinent component yet. So, but as I mentioned, I do not deny the contribution of the mid-oceanic ridge basalt, and so
But my point is anticontinent is one of the major components. So.
Any other questions?
Yoshi, I didn't quite follow why anticontinent should be more dense all the way through the mantle. Usually we think of Restite, parts per guide as being less dense. Can you elaborate on that a bit?
That is probably caused by high mafic component, more mafic than the mid-oceanic ridge basalt. That is, the MgO is higher and the FeO is higher, and also silica is poorer. So that means the formation of the magnesium perovskite earlier than the mid-oceanic ridge basalt component. That is our interpretation for the density difference.
Any other questions? Perhaps I could just ask one question, which is the anticontinent being equivalent to EM1 showed that the average sort of years suggests that the process was much more efficient. I was asking that equating the anticontinent with EM1, and then the EM1 has a rough age of 3 billion years. Does that suggest that this process was much more effective early in the Earth's history?
Yeah. The 3 billion years that we calculated is the integration of formation of continent for 3 billion years. Okay, so that is average age is 1.5 billion. That's the answer to you.
A question over there.
Okay, for that question, we published a paper in Journal of Petrology about 3 years ago, and also next paper will come soon. The conclusion of our study is calc-alkaline magma is, of course, a mixing product between crustal-derived component and basaltic, mantle-derived basalt component. And thoracic magmas that are products from lower crustal melting. So mantle-derived basalt magma causes partial melting crust to form thoracic magmas. And also, such a thoracic felsic melt mixed with mantle-derived basalt to form calc-alkaline andesites. Is that answer to you? You mean, I do not really understand what you said, but in our volcanoes, generally we have two types of andesite in a single volcano. One is calc-alkaline and one thoracic. And these are all derived from, essentially derived from, or originally derived from mantle-derived magmas, but thoracic magmas are reheating product or remelting product of the crust. So I don't really understand what causes the differences. You say, what causes the difference between what? Well, okay.
Well, thanks very much. I think we should draw to a close. I'd like to perhaps give one more round of applause for Tatsumi for San.